This time, as mentioned previously, I will begin by explaining the process of network calibration before delving into transit assignment. First, before conducting the network calibration process, I will make a copy of the base scenario where observed traffic volumes are input. I will name this new scenario net calibration. The reason for copying the scenario is to have a backup of the original data, allowing us to protect it from various changes and altered situations. In general, network calibration is typically performed within the influence zone, which can be divided into the analysis zone and the influence zone. The analysis zone refers to the entire scope of the demand analysis model, while the influence zone is a concept that represents a spatially narrower area compared to the analysis zone. It denotes the area where significant changes in traffic patterns occur due to project implementation. The influence zone can be further categorized into direct and indirect influence zones. The direct influence zone refers to the area adjacent to the project implementation region, where detailed OD information or a detailed network is required due to the project's impact. The indirect influence zone, on the other hand, encompasses areas that are not directly within the project implementation region, but experience changes in travel patterns due to the project, and are therefore included in the benefit assessment for economic analysis of the project's effects. For example, when analyzing a new road project that connects Morogoro and Dodoma, the direct influence zone would be the area where the new road connects with interchange. The indirect influence zone would include regions such as Dar es Salaam and Challenge, as well as areas around the project route, where the project's effects are expected to occur. The analysis zone would cover the entire country of Tanzania, as it's the overall scope of the analysis. The establishment of the influence zone involves predicting the extent of a project's effects. Typically, 3 criteria are applied in determining the influence zone. Let's briefly examine these 3 methods for setting the influence zone. The PV method sets the influence zone based on the ratio of specific destination arrival traffic volume to the generated traffic volume, with regions where this ratio exceeds a certain threshold being considered part of the influence zone. The DV method establishes the influence zone based on regions where the traffic volume change on road segments due to project implementation exceeds a certain threshold. The RV method takes into account the traffic volume change rate on road segments resulting from project implementation. Below are the formulas representing these 3 methods for setting the influence zone. Usually, the establishment of the influence zone is carried out after the network calibration for the base year is completed. This implies that network calibration needs to be conducted effectively to ensure the accuracy of the influence zone's definition. Network calibration is also referred to as network validation. Network validation involves implementing current travel patterns within the model, typically by comparing them with observed volumes. In network validation, model-assigned volumes are adjusted by iteratively modifying parameter values until they fall within an acceptable error range compared to observed traffic volumes. This process ensures the adequacy of the model. In the standard guidelines, network validation is typically performed to achieve an acceptable error rate, ranging from plus or minus 15 to 40, depending on the level of highway observed volume. The method for calculating these error rates involves taking the difference between the assigned volume and the observed volume, and then dividing this difference by the observed volume. The result is then converted into a percentage by multiplying it by 100. The table below provides allowable error criteria for different traffic volume levels. Typically, different error criteria are applied depending on the observed traffic volume, with an observed traffic volume of 5,000 vehicles serving as a reference point. For road expansion projects, there might be observed volumes within the project segment. Therefore, an allowable error criterion of plus or minus 15 or 20 is applied to the project segment's volumes. For adjacent roads, allowable error criteria range from 20 to 25. Other major are subject to allowable error criteria ranging from 30 to 40. In this context, adjacent roads refer to roads that could be competing or connecting routes to the project route. These roads may directly compete with or complement the project route. Other major roads refer to those roads included within the benefit assessment area, meaning they are considered in the economic analysis of the project's effects. In addition to individual link error rates, the guidelines also set a requirement for the correlation coefficient to exceed 0.8 for the entire calibration points. The method for calculating the correlation coefficient will be demonstrated using Excel later. Now let me explain how the network calibration process is conducted. For reference, I have already entered the observed volumes into the viewpoint column as follows. As you can see, I have collected and inputted observed volumes for highways, urban expressways, and major road access, totaling 16 observation points. To perform network calibration, it is essential to have such observed traffic data, and to compare it with the assigned volumes, we need to run the model. So first, let's perform network data inspection, and then proceed with the highway traffic assignment model, as I mentioned in our previous session, before executing the highway assignment. You need to set the highway assignment parameters. Ensure that the value of travel time is set to 1.0, the OD matrix time duration is 10.0, and check the values for occupancy and passenger car equivalent before clicking OK. Run the highway assignment model. Select the trip matrix. Choose volume delay function for each link. And then go to the Run options. Check the Include Turn Volume and Path Analysis option. In the stopping criteria, set the relative gap to 10 and click OK. Under Output Information, select Overwrite and then run the model. Following this process, you will have the assignment volumes output for the links. As I mentioned previously, observed volumes are in vehicle units, while assigned volumes are in PSU. To compare the two traffic volumes, you need to convert the assigned volume into the same units as the observed volume. This unit conversion process can be done using Excel or can be performed within TOVA. During the explanation of TOVA's basic functions, I demonstrated the column addition feature and column operation function. Now I will show how to use these functions within TOVA to convert the units of observed traffic volume and calculate the error. For the demonstration, let's start by adding a column. The column name will be SAinvolve. After adding the column, execute the calculate field function and enter the formula into the set field. The formula should sum the values of PSU-based volumes divided by PCA for each vehicle type, resulting in the total traffic volume in vehicle units. In the where section, I can input constraints, but I want to apply the formula to all links, so I will leave this section empty. After that, click OK. Now let's examine the calculated results. Click on the header of the ID column to sort it. If you look at the assignment volume for ID number 60,111, you will see that the value in the TOVA column is approximately 1215 PSU. If you convert this assignment volume into vehicle units, it's about 1109 vehicles. This time, let's go through the process of comparing it with observed volume. Once again, click on Add Column and add a column named Error Rate. After adding the column, run Calculate field and input the newly added column at Update field. In Set, we will input the formula to subtract observed volume from assigned volume, divide the result by observed volume, and then express it as a percentage. Here, we will add a constraint to calculate only when observed traffic volume is greater than 0. So, in the where section, we specify the constraint that V-point should be greater than 0. Now click OK to proceed. Now when you click on the error rate column to sort it, you will see the error rates calculated as shown. If you want to view only the linked data for locations where observed volumes exist, you can use the search function. Click Search Enter the condition where point is greater than 0 in the constraints box and click OK to extract and view the link data for network validation points. Looking at the error rates for the assigned volumes, you will notice that the maximum error rate is 9 and the minimum is -8.9. These error rates are within the 15 tolerance range specified for project segment standards, indicating that the model adequately represents the traffic conditions. Further network validation may not be necessary, but I will continue this session for demonstration purposes. I am going to drag the error rate column to the left to view it alongside the link type. We do this to assess whether specific types of links have been assigned more or less traffic, helping us analyze the distribution. When looking at link type 101, we observe both positive and negative error rates. However, since all of the error rates fall within the acceptable error margin, there doesn't seem to be a significant concern. Next, let's look at the error rates for link type 102, the urban expressway. You can see that the urban expressway has relatively low traffic assignments. If a particular link consistently has low traffic assignments and exceeds the allowable error range, you may need to adjust the parameters for that link and then perform another assignment to increase the assigned traffic. To increase or decrease assigned traffic, you can adjust parameters such as capacity, speed, alpha and beta. But typically, the alpha and beta values are not adjusted, while capacity and speed are modified to perform network assignments. Adjusting parameter values like capacity and speed to match assigned traffic with observed traffic is possible, but there are limits to how much you can increase or decrease these values. There are regulations and guidelines in place to provide a recommended range for adjusting parameter values, as shown in the table I mentioned. As you can see, when FNID is 3, the alpha and beta values are set to 0.57 and 1.68 respectively. The standard travel speed is 98.3 and the standard capacity is 26,000 for one day. This time, let's practice adjusting the parameters of the urban expressway that was previously estimated with low assigned volume to increase the volume. First, let's check the FNID for the urban expressway in the link data table, which appears to be 7. To adjust the parameters for FNID 7, let's review the parameters and the allowable range as indicated in the Excel table. For FNID 7, the parameters are alpha 0.48, beta 2.4. The speed can be increased up to 100.0 and the capacity can be increased up to 28,205 based on a daily rate. However, keep in mind that the capacity in the link data is expressed in hourly units. Since we applied a conversion factor of 10.0 to transform it into a daily rate, so we can adjust the 1-hour capacity up to 2821 PSU. Now let's increase the speed and capacity around the section with observed traffic volumes on the urban expressway, which is FNID 7, link type 102 to the upper limits of the allowed criteria. After that, We will rerun the traffic assignment and compare the new assignment with the previous one. Right-click on the relevant column in the link table and choose Zoom to zoom the map to the specific section. Then, go to the right side and choose Draw Setting Link and select by type to easily identify the urban expressway line. Now click on the link info icon at the top and select the links in that section. In the sub-window, enter 2821 for capacity and 100 for speed, and then click Save. Do the same for the links in the opposite direction. Also, make sure to change the connected sections before and after this point in the same way. With these settings, let's run the highway assignment model again. Select all modes in the trip matrix. Choose each link for the volume delay function. And click OK for Run option. Set the stopping criteria to a relative gap of 10, just like before, and click OK. Keep the output as overwrite, and then click OK. Now run the model. Once the assignment is completed, you can add a column to convert the assigned volume to vehicle units. Let's name this column Assign Volume Vehicle 2. Open the menu, go to Calculate field, choose Assign Volume Vehicle 2 for Update field, and input the formula to convert PCO to vehicles in the set field. Auto plus taxi plus divide bus by 2 plus divide other truck by 3 plus small truck plus divide medium truck by 2 plus divide large truck by 3. After you have completed the input, click OK. Drag the Assign Volume Vehicle 2 column with your mouse to move it next to the Assign Volume Vehicle column. When comparing the first assigned traffic volume to the second assigned volume, we can see that the assigned volume for ID 73,345 has increased by approximately 1,600 vehicles. However, on the opposite side, for ID 73,349, the volume has not increased at all. Since we only increased speed and capacity for short segments of the entire road network, it appears that these changes did not have a significant impact on the overall travel time. Indeed, in practical network calibration, it's common to adjust parameters for longer segments or entire road axes rather than focusing on short segments. This approach ensures that changes have a more noticeable effect on the overall network performance. Now I will show how to adjust the parameters for the entire urban expressway segment, specifically for links within ID 7. First, open the Calculate field dialog to make these changes. Select Speed for the Update field. Enter 100 in the Set field. Enter the constraint as if in ID equals 7. Click OK. This will set the speed to 100 for all links within ID equal to 7. Next, choose Capacity for the Update field. Enter 2821 in the Set field. Keep the condition the same, if in ID equals 7. Click OK. This will set the capacity to 2821 for all links within ID equal to 7. Let's add a column to convert the next assigned volume into vehicle units. You can name this column Assign Volume Vehicle 3. In this state, let's rerun the highway assignment model. From the trip matrix, select All Modes. In the volume delay function, choose each link. Click OK. For the stopping criteria, relative gap, set the value to 10. Click OK. For the output, choose Overwrite and click OK. Now we can proceed to run the model by clicking the Run button. Open the menu, go to Calculate field, choose Assign Volume Vehicle 3 for Update field, and input the formula to convert PCO to vehicles in the Set field. Add passenger cars, taxis, and small truck as they are. Divide other buses and medium truck by 2 before adding them. For other truck and large truck, divide by 3 before adding. Once you've completed the input, click OK. Now, using your mouse, drag the Assign Volume Vehicle 3 column to the right of the Assign Volume Vehicle 2 column. Let's compare the volumes. The volume for ID 73,345 has increased by approximately 1670 vehicles from the initial assignment, and the volume for ID 73,349 has also increased by 207 vehicles. If you were to visualize the impact of the current parameter adjustment on traffic volume through a link thematic map, you would be able to quickly discern which links have experienced increases or decreases in traffic volume. This visual representation can be a valuable tool not only for understanding the current adjustments, but also for guiding next parameter adjustments. Before creating the link thematic map, Let's add a column to input the difference between the two assigned traffic volumes. You can name this column Assign Volume Difference. Now put Assign Volume Difference on Update field in the Calculate field menu. In the Set column, input Assign Volume Vehicle 3 minus Assign Volume Vehicle and click OK. In the main menu, go to Themes and select Link, then choose Classification. In the column section, input as symbol diff. Set the classification to have 3 classes. Specify that values less than -1 should be displayed in blue, values greater than 1 in red. And uncheck the box for the range between -1 and 1 to hide it. And then click Draw. As you can see from the link thematic map, it's important to keep in mind that if traffic volume increases on one route, it often means a decrease in traffic volume on competing routes. That's correct. If you can track where the traffic passing through validation points on the urban expressway comes from, where it's going, and which routes it's using, you can make informed decisions to actively manage the network by adjusting capacity or speed along specific routes to optimize traffic flow. Certainly, if you can track the traffic passing through validation points on the urban expressway and understand its origin and destination as well as the routes it uses, you can effectively perform network calibration by adjusting capacity or speed along specific routes to manage traffic flow more efficiently. We will now perform a path analysis of the traffic passing through the validation points. The reason for the warning message is that Include Path Analysis was not checked in the Run option when running the highway assignment model. In the current state, let's go back to the highway assignment model and rerun the assignment with Include Path Analysis checked. After completing the highway assignment, click on Path Analysis in the main menu and select Highway selected Link Analysis. Click on Map, then select the validation point on the map and click Search. Now, we have identified the movement paths of traffic passing through the validation points. Based on these movement paths, we can proceed with the area path analysis. As you can see, we can identify alternative paths in addition to the primary route through the validation points. Adjusting parameters for these alternative paths could potentially increase or decrease traffic volumes on the primary route through the validation points. However, in this particular case, with relatively low traffic volumes, the impact may be limited. Up to this point, I've provided an explanation of one method for network calibration. In actual work, there are situations where even with repeated iterations using this method, it's challenging to achieve convergence within an acceptable error range. When zone size is large, they may not accurately represent internal traffic movements in the traffic assignment, resulting in lower traffic volume representation. In such cases, one can subdivide zones to increase intrazone traffic volumes. To execute zone subdivision in TOVA, go to the main menu, click on Tools, then Zoning and select Division. If you want to subdivide Yoxamon at this point, clicks and then Map in sequence. On the map, click on the zone node for Yoxamon. Next, you will need to decide how many subzones to create and the criteria for subdivision, but this decision requires pre-existing data for dividing weights. I will briefly explain how to build data for zone subdivision. The first criterion for subdivision is determining the subdivision ratio based on detailed population data for specific areas. The second criterion, if the first data is unavailable, involves establishing the subdivision ratio based on urbanized area or land area. Since detailed population data for this area is unavailable, I've decided to subdivide it into 3 zones with arbitrary ratios. After entering the ratios and clicking Map, you can determine the locations for subdividing the zones by clicking on the map. Checking Generate Zone Connector will ensure that the zone centroid is connected to nearby links. Once the zone subdivision is complete, you can verify the ID of the subdivided zone by selecting Info from the icon and checking the vehicle trip OD table to see the specific OD for that zone. Taking into consideration the time required for model construction and execution, it is a common practice to perform zone subdivision only in the areas where detailed OD and network construction are necessary. Typically, this is done in the project areas, which directly impact the model, rather than subdividing all regions. Up to this point, I've introduced how to perform network calibration and validation within the TOVA program. Now, I will briefly explain how to use Excel to organize the results of network calibration. To organize traffic assignment results using Excel, you can first use the search feature in the link table menu to select and export only the linked data with observed volume. Then, you can import this data into Excel for further analysis. Enter the constraints point is greater than 0 and click OK. You will notice that out of a total of 4,209 records, 16 have been selected based on this condition. In this state, you can save the selected records as a text file. Click on Export in the menu. Enter a file name. Check Select All. Click OK. Now you can open the file in Excel and apply a formula to convert the volume into vehicle units. Create a header like ASCII volume vehicle 4 and input the formula. Then copy it to the remaining cells. You can also cut the cell and insert it next to ASCII volume vehicle 3 for comparison. You can add a cell next to it to calculate the error rate. Using Excel for such tasks indeed offers the advantage of time efficiency. Once you've entered the formula, you can easily copy and paste it to save time in repetitive tasks. In the next iteration, you can export the file, and by copying and pasting this formula, the calculations will be automatically completed. This makes your workflow more efficient. After completing the network calibration, I will now explain how to calculate correlation coefficient values as mentioned earlier in this session. To calculate the correlation coefficient in Excel, you can use the RSQ function. Here's how to apply it. Input R as Q function in a cell and specify the range that contains the observed volumes. Then specify the range for the assigned volumes. Press Enter. As a result, you will get the R² value, which in the example you provided is 0.988. Indeed, in the final stages of network calibration, it's essential to check whether the model's error rate exceeds the acceptable margin and whether the correlation coefficient surpasses the desired threshold, such as 0.8. You should provide the observed volume, assigned volume, error rate, and the correlation coefficient value at this stage for assessment and reporting. With that, I conclude the explanation and demonstration of network calibration.